Today we're going to problem 11, 13, 20, 22, and 30 in chapter 5. For problem 11, a circular loop of wire carrying a current I is located with its center at the origin of coordinates and the normal to its plane, having spherical angles. There is an applied magnetic field like this. And part A, calculate the force acting on the loop without making any approximation. Compare your result with the approximate result. Comment. And our magnetic field is like this, and the normal vector of the current of the circular loop be right in N here, and the force on the D force of the loop will be like this, and the total force will like be integral over the loop, and we calculate in every 3 directions individually. And here we change our integration into we use the Stokes theory. And finally, you calculate the 3 components of the force equals to our force in x direction will be IB0 times beta sine theta 0 sine phi 0 times pi a square. This is area. And our y direction will change sine into cosine, and we have no amplitude in z direction. And next, we compare our results with 5.69, and we write down our magnetic moment, and use the formula like this and calculate the same. We will get the same answer here. And next, we calculate the torque. For lowest order, we just use we take our B field. B field is equals to B0 in X direction and B0 in Y direction. And use the formula, we will get the answer will be like this. We can calculate our exact torque with the formula like this, and after some heavy calculation and change our coordinates between the Cartesian coordinates and the new coordinates with the corresponding is theta 0 and phi 0. And finally, you'll get the answer like this, and it's quite equal. The value is equal, and the final comment is that the shape is invariant as long as the area remains the same and the figure lies in the same plane. The shape is other shape is okay if the areas remain the same. And for 13, a sphere of radius a carries a uniform surface charge distribution sigma. The sphere is rotated about diameter with constant angular velocity omega. Find the vector potential and magnetic flux density both inside and outside the sphere. And our velocity omega rotates along the z-axis, and our omega equals to omega z-axis here. EK is z axis, and is our position vector. And we calculate our surface current density. And next, calculate our vector potential. And next, we change these two components into spherical harmonics. Okay, change into spherical harmonics, and we consider the coordinate, the orthogonal relation, and finally we'll get the answer here. And next, we're considering the outside and the inside field, inside potential. And next, calculate the magnetic field. And finally, the answer will be like this one and this one. This is the inside magnetic field. This is the outside magnetic field. Next, we're going to problem 20. Starting from the first equation 4.12 and the fact that magnetization M inside a volume V bounded by a surface S is equivalent to a volume current density Jn here, and the surface current density show that the absence of macroscopic conduction currents, the total magnetic force on the body can be written like this. Okay, and first we calculate our force. We write down our force in the form like this, and the integral will be write down in the volume integral and the surface integral for the force, because we have the volume current density and the surface current density. So we have the two kinds of force here. And expand our J and K. It will be like this, and change the position. Okay, and here, this one is the Jacobian matrix here. And next, we use some identity to help us to calculate the force. Next step, we use these two identities to help us to treat these two terms, and we can sorting them into this one, and this one will cancel each other, and finally we'll get this one. And next, the last identity we used in part A. This is our last identity, and again we're sorting our formula. Going to next step, it will be like this, and this one and this one will be cancel each other, and this one will go to 0 because here we have the divergence of the B field here. We're going to 0. So finally, we will get the relation here. And for part B, a sphere of radius r with uniform magnetizations has its center at the origin of coordinates and its direction of magnetization, making spherical angles. If the external magnetic field is the same as in problem 11, use the expression of part A to evaluate the components of the force acting on the sphere. Okay, so we just calculate the force directly and finally get the answer here. Okay. And going to next for 22. Show that in general a long straight bar of uniform cross-sectional area A with uniform lengthwise magnetization N when placed with its flat and against an infinitively permeable flat surface adheres with a force given approximately by the formula here that related your discussion to the electrostatic considerations in section 1.11. And from problem 19, we can take the delta Z approach 0 and our B field will get the form like this from problem 19. Okay, and our magnetization N has the direction in Z direction, and the force will be like this. And again, we have a uniform magnetization inside here. So the first term will go to 0, and that's our surface integral. Our surface integral will only left on the end surface. We only have values on the end surface. So our final answer will be like this. Okay, and it approximates like to this one. If the L has much larger than A. And finally, we're going to problem 13. So 30, part A, show that a surface current density here and flowing in the actual direction on the right circular cylindrical surface of radius r produced inside the cylinder uniform magnetic inductions here in a direction perpendicular to the cylinder axis. Show that the field outside is that of a two-dimensional dipole. And we just calculate our vector potential directly and expand our current here and write down and our 1/r right in spherical coordinates. Expand in cylindrical coordinates will be like this from the formula 3.149 in Jackson. Okay, so we just expand, and here we take a look inside this, and only the n equals to 1 will survive after the integral. So this one, only the n equals to 1 will survive. And next we just keep calculating our integration. And finally, and next we use the relation here. We change our this one. We change our which one? This one into this one. So we're sorting our vector potential like this, and use the formula for a small k though from the formula 3.102 and 103. We can change our special function into gamma function here, and gamma 1 equals to 1 and gamma 2 equals to 1, 2, and gamma 1 and gamma 2 are both equals to 1. So finally, we sorting our integration will be like this, and because here we have a delta k, and we double because the shape of the integral is the same, so we double, and we double the integration domain from, we change our integration from 0 to infinity to change it into minus infinity to positive infinity, and we have to divide by 2 to balance the value, and finally we will get the answer here. And next, so our vector potential inside and outside, we have the form like this, and next we calculate our magnetic field easily. We have the answer here, and finally we check our outside vector potential, and sorting into the form like the form of the dipole. The form of the dipole contribution, and we can calculate the dipole moment. It will be like this. There's only one minus, no double minus. This is a minus. The answer is minus pi rho I r and y direction. And next, calculate the total magnetostatic field energy per unit length. How is it divided inside and outside the cylinder? So we just integrate we have used the formula 1 divided by 2 mu 0 and integral the B field square over the space, both inside and outside. And finish the integral, we'll get the answer here. And for per unit length, we have the energy stored in field like this. And what is the inductance per unit length of the system? View as a long circuit with current flowing up one side of the cylinder and back the other. A long circuit. Since we have only the circuit power energy equals to this one, and we divide by L, and we use the value from part C, and we will get the answer here. So for chapter 5, we are finished.